I thank everybody for joining our monthly building electrification webinar. This is our fourth year of monthly programs. I'm Steve Miller, tonight's host. I have started recording, and we've covered over the 4 years a broad range of electrification topics, which are all online. And in a couple of days, I will email the links to tonight's recording and slides to all who have registered. And tonight we have a very special guest. It's a summer vacation type of topic. This is a story about a family's adventures in design and use of an electrified EV. The title that you're going to see from me is slightly different than him. We have not coordinated titles, but this is um, a story by Professor Ben Wymore, who describes his efforts to design and resulting adventures in driving his electrified RV, which I call a house on wheels. So for many years, he and his family have enjoyed traveling to remote sites in the US and maybe elsewhere. And he joins us via Starlink, which seems to be doing very nicely from someplace, he said, about 100 miles south of the Nevada border, and it's doing fine. So he's going to describe both his RV design enhancements and also his off-the-grid travel adventures in his electrified RV. So Ben, it's your turn to take it away.
Okay. All right. Thanks, Steve. And thank you very much for having me. My parents actually met in the Sierra Club, so I think this is it's nice to be able to be involved in the Sierra Club event. My father was a hike leader in California, and my mother had moved from New York out to California, and that's how we met. So yeah, I'm going to talk today about.
Hey Ben, sorry to
RV.
interrupt, but we can't hear you. Yeah. You're extremely faint.
Oh, the audio is low. Okay.
I'm hearing him just fine.
Yeah, it's
For
fine.
me, it's fine too.
Yeah, he's good at this end.
Okay for me too.
Okay.
Whoever spoke should increase the loudspeaker volume. That would be an adjustment you can make. Lower left corner is audio, and you should go to audio settings.
So I'll try to speak a little bit louder. Yeah, I don't have my I don't have like a microphone. I'm just using the laptops. You know, we're on the side of the road on US 395. So yeah. Okay, so yeah, just to give you a little bit of background. So my wife and I got into RVing in the late 90s. Kind of a funny story, but I'll spare you the details. Suffice it to say, we RV'd for a number of years. When we lived in Oregon at the time, so we'd go to the coast, we'd go to the mountains. Very quickly became interested in dispersed camping. So most of the land in the Western US is owned by the federal government and is administered either by the Bureau of Land Management, BLM, or the US Forest Service. And details aside, so long as you're not blocking a road, you can camp anywhere you want on federal land, unless it's otherwise signed. And then you do have to, typically you have to move about 25 miles every 14 days. That's sort of an anti-squatter policy, okay? So we moved to New York and didn't have an RV for a number of years, bought one in about 2012, did some summer trips with our children. And then in the summer of 2013, our children were 9 and 12 at that time, we decided to travel for a year. So I resigned my job as a software engineer at Crestron, and we went on the road. And the expectation was that after a year, you know, the money would run out and then I'd go back to work. Well, a funny thing happened. It turned out actually that because we were renting out our house in New York, after a year, we had more money than when we left. So we said, okay, well, let's just do this for a second year and then a third year. At that point, our son was going into high school. And so we decided to come off the road, unrent our house so that our son could experience, have a high school experience. So with that, this is what you're seeing here is a trip map, and the 3-year trip. And I'll share a link for all this at the end. But this red and blue line you're seeing here, this represents each day of travel for the 980 or so days we were on the road. And on our website, you can click on these and it will take you to the blog for that day. It'll say day 573, and it'll have pictures and talk about, what we did. So as you can see, we spent a summer up here in Alaska. We spent a summer in Nova Scotia, and we'd winter generally down in the desert Southwest. So the theme was sort of like 68 and sunny every day of the year. So as it got too cold, we'd go south, and as it got too warm, we'd head north. And then these other colors are various other trips. And for the last 5 summers, including this one, I have traveled for 4 of them solo, and my wife joins me for a portion of those as well. Okay, so I just want to cover some fundamentals before we get into, and by the way, if you have a question, if you just raise your hand using the reactions in Zoom, I'm very happy to answer questions like in line. All right. So I apologize because I don't know what everyone's background is here. So I'm sure this is review for many of you. Usually when I talk, I know what everyone knows, or at least what they should know, because I talked the last time also, right? So, all right. So here, I just want to mention that in terms of electricity, the wattage of something is the voltage times the current. And these are somewhat interchangeable. In other words, I can have, well, let me first talk about what voltage and current are very briefly. So if you think in terms of a water hose analogy, so voltage is the pressure at which the water comes out, and current is the volume of water. Okay, so I can have, if you imagine like a squirt gun, okay, fairly high pressure, very low volume, so that's like high voltage, low current. If I have you've seen these rubber above ground swimming pools that people have, right? So if you were to walk over to one and just cut it with a knife, so there would be a very large volume of water, but a very low pressure. So that's high current, low voltage. And these are exchangeable using transformers. So I can have 1 amp at 100 volts, and I can convert that into 10 amps at 10 volts or 100 amps at 1 volt. And we'll see why that matters. Okay, so in an ideal world, I would have painstakingly designed an RV and figured out I'd use triple windows and all sorts of insulation and like that. But that's not what happened. Instead, what I did was I went on Craigslist and I bought this truck camper for $900. Now this thing is like 4th hand, and there's like water damage and stuff like that. So the question was how to turn this into something that is 4 seasons livable. Okay. And this is what it looked like on the inside when I got it. It was a little bit scary, but we got to work, and I'll just share with you briefly some of the modifications that we did to get us to where we needed to be. So here's what the inside looks like facing to the rear, and you can see this is like a dresser, or I don't know what you call it, like a whatever, you hang clothes in it, a closet. And let's move this out of the way. Okay. And so the first thing we did was tear that out. And what you can see here is the last guy that owned it, he took the place where the propane tanks live and he made an enclosure for a generator. So he moved the propane enclosure up into the closet, which is now visible because we tore the closet out. So here's the view from the outside. And I basically just took the propane enclosure out, put it down below again. And now we have a hole that goes into the side of the RV. And so patch that up with some metal here. Okay, and it ends up looking like this. And then, you know, we took this and turned it into this with, you know, paint and got some fixed up the drawers, etc. The water heater. So typically an RV water heater is 6 or 12 gallons. It's propane operated. And the thing about it is that you're using up propane in order to heat up 6 or 12 gallons of water that you may not necessarily need to heat up. And also that 6 or 12 gallons of water is locked in the sense that it's between your freshwater tank and the hot water spigot in your sink. So you can't use that. So in our big RV, which I'll show you a photo of at the end, I modified the water heater to put a spigot on it. So if we were out in the wild and we ran out of water, I could actually drain the hot water heater back into the fresh water tank and use that water. Okay, but what I did here, like I said, the water heater came broken. So this is an instant hot water heater, which is used for washing livestock. You can buy this on Amazon for like $60. And it says here, like, not for indoor use. So I put a mirror over that so I wouldn't see that warning sign. And then when you use the shower, you just, there's a ceiling fan. There's a skylight in the bathroom, and I put in a powered fan, and I just put it on exhaust mode, so all the carbon monoxide hopefully goes right out. And even if it doesn't, you get kind of lightheaded when you're showering, so it feels like a wonderful experience. So this works pretty well. Here we are now, I've removed that closet, right? And the propane thing is below here. And then we're building out this framing. And the reason we did all this is because I fly a paramotor, which is this ultralight. You strap this thing on your back and it has a propeller on it, which is removed right now. And then you start to run and you're clipped into like a parachute-like wing and you run off the ground and then you can fly around. And so it's very, in Rockland County, it's kind of a pain. You have to travel for almost an hour to get to an airport. But when you're out in the middle of the desert, it's really great. You just go out in the morning, say, oh, I wonder what's behind that mountain, and off you go. So there it is, strapped in. Another thing with RVs is that the way that water pressure is generated, and as was mentioned at the beginning, you know, an RV is really just out. So whenever I say RV, you can just replace that with off-grid tiny home, or you know, if you're trying to build a cabin off in the woods. So all this is really quite relevant for that. So typically there's a freshwater tank, a pump, and then when the pump has a sensor. So the moment that you open the spigot, the pressure between the pump and the spigot drops, the sink faucet that is, and so the pump comes on. And sometimes it'll kind of like do this on off thing, and the water kind of comes out in a pulsing kind of way. And so I wanted a more residential experience. So I installed this. This is a pre-charged pressure tank. So this is about the size of like a Culligan water tank. And along this midline, it has like a butyl, a piece of butyl rubber, like a diaphragm. And it has a Schrader valve, like for a bicycle or a car tire. You inflate the backside with, let's say, 60 PSI of air, and that pushes the butyl membrane all the way up against the input, the water input, which is on the top here. And then what happens is the pump pushes the water in, and that is pushing that membrane down. And when the air pressure on the backside of that membrane equals the max pressure that the water pump wants to see, so then the pump stops running. Okay, so what I can do is I can run the pump, and the pump runs and runs and runs and runs and runs, and you can hear it straining harder and harder, and then eventually the pump stops. At that point, you just turn the pump off, and now when you open your sink, that air under the membrane is pushing the water out into your sink faucet. So, and this will typically last for a single person, like, I don't know, 2-3 days, let's say. So you just run the pump once, and then after that, the water just comes out silently and at a constant pressure. The refrigerator and the stove are propane, as is the instant hot water heater for the shower. And so propane, if you're familiar with your grill, it has a regulator, right? So you have a hose you hook on, and then at some point between the propane tank and your grill, there's like this little round silver thing. It's about this big, and that regulates the propane relative to the air. And propane pressure should be about 11. I think it's 11 inches of water. The amount of pressure that is required to raise water 11 inches in a tube. And so at high altitude, the refrigerator stops working. In fact, the refrigerators, all these RV refrigerators say not for use over 4,000 feet of elevation, but I'm at 11,000 feet of elevation. So what's really happening is because there's less air pressure, the propane pressure is higher relative to the ambient air pressure. So you have a mixture, a fuel-air mixture, which is too rich. There's too much fuel in the fuel-air mixture, and that prevents combustion. And so by using this is a manometer, if I remember correctly, is what it's called. And this measures relative air pressure. So you can see it's measuring the pressure of the native air here and the pressure on the propane. And as you can see, I'm at a high number here. And so there's a little cap on the regulator that you can take off, and you can adjust the regulator. It says like don't remove. So you remove that, and then you can adjust the pressure on the regulator. And so this way I can set, even when I'm at 10,000 feet, I can set that propane pressure back to 11 inches of water, and then the refrigerator works just fine. You just have to remember to set it back when you go down to sea level. You're always going to be, you're using a lot of water. And so what I did here was we have a pickup truck, which has like a full back seat, a crew cab. And so I built this floor, and this is like, if you imagine like a water bed for a large child. And this holds about 60 gallons of water. So I built this frame and then put a top on it here. So now I can load up all my stuff in where the back seat was, and it's a nice flat, even surface. I just unbolted the back seat from the truck. And then I can fill it here with 60 gallons of water. And that way, when I'm out, if I use up the, I believe the native water tank on this truck camper is about 24 gallons. So if I use up the 24 gallons, I have a transfer pump, and I can transfer the water from here back into the truck. As I mentioned, the refrigerator on an RV runs on propane. It can also run on electricity, but it is not a condenser-based. So I have a question from Wesley. If you just if you just use the like raise your hand thing, that way I don't have to keep looking at the chat window. I guess I can just leave the chat window open too. So Wesley, I did cover this earlier. I am coming from a computer science background. I worked as a software engineer for about 15 years before we went on our 3-year RV trip. My wife has a degree in psychology, and she founded and operates a Montessori school in our hometown. So that's where we're coming from. But my father was more of an electrical engineer, and had I gone to a technical college instead of a liberal arts school initially, I'm sure I would be an electrical engineer and not a computer scientist, because I much prefer soldering things together than writing lines of code and using power tools. So the refrigerator, it doesn't use a compressor like an air conditioner does. It has a heating element, propane or electricity, and that causes ammonia to evaporate. And when the ammonia literally condenses, that's how the cooling is done. Okay, and that's so you don't need electricity. You can just run a refrigerator on propane. So modern RVs, they have a fan system that comes on at a certain temperature to the heat rises up along the back of the refrigerator on the outside of the RV, so to speak. I mean, you can't see it; it's behind like a panel, but it's not in the food part, obviously. And there's a fan, the exhaust fan, that sucks the air up. So this one doesn't have that, so I built one. And what I did was I took a laptop cooler, like you put your laptop on it, and then it has fans that shoot air into the bottom of your laptop. And I just took the guts out here and put it onto this piece of wood. And because it was made for a gaming laptop, one of the side effects is that you get cool lights. So it does this when it's running. And so that means at night, when you're looking at this is the exhaust vent of the refrigerator, you can see the blue light if it's on. Okay, so that after all that got us from something that looked like this to something that looked like this. Okay, so not too shabby. The refrigerator was missing. Some of the trays were broken, so I drew these up in a CAD program and 3D printed them, and that worked out quite nicely. These are the tie downs, like these metal eye bolts that hold it down, but the wood underneath had rotted away, so I cut the fiberglass skin of the RV and removed this wood here, and then this is an aluminum L channel that's over the rotting wood, which is over the actual aluminum frame of the RV. So I'm just stabilizing that rotted wood below, and then the bolt goes through, and now the theme of this RV is that with enough caulk and some sheet metal, you can solve almost any problem. Okay, so now we get to actually more of the relevant stuff in terms of electrification. So RVs, even to this day, come with air conditioners, roof-mounted air conditioners, and they are just functionally, they are equivalent to like these $200 air conditioners that you would buy at Walmart 20 years ago. They're either on or off, and they're just very loud and not particularly energy efficient. So that had to go. So we're removing the rooftop air conditioner, and this is the top half and this is the bottom half. And so now we have a skylight. And so we fixed that by putting in, this is a powered vent. So now you can vent the air out. And if you're wondering why there's a tire on my roof, I have the first version of the Starlink dish, which is a round dish. It's about 18 inches in diameter, and I wanted to mount it on the roof, but I didn't want people to be able to see it. So I actually screwed this tire into the roof, and then I laid the Starlink dish on top of the tire. So from the ground, if you're looking up, you just see a tire and you assume, I guess, that there's a spare tire on the roof of the RV. But really, it's to conceal the Starlink dish. Of course, this had to go because we're about to cover the entire roof with solar. So here I am laying out the panels. These are the 3 panels that are off of our big RV. And then I had, these are 185 watts each. And these are the 400 watt panels I had on the truck camper. And so then what I did was I added another 7 panels. And this is roughly the size of the entire roof. And I've left this little spot for where the Starlink dish is going to go. And then it's just a matter of getting some aluminum L channel and designing some beams, I guess you'd say, to lay all of these panels on. And here we are starting to mount them. And so here is the final result. This is on the banks of the Missouri River near Ocala, South Dakota. And you can see the 11 solar panels as well as the Starlink. This was sort of Starlink. The problem with Starlink is that the dish needs to have a software update every month or two, and you cannot update the software like by way of a computer. It has to download its software update from the sky. And so what that means is that I have to take the Starlink dish off the RV because where I parked the RV. So I'm the only person in Rockland County that probably got a ticket from the from the zoning inspector for violating the more than one RV on your property rule. And so what I had to do was, I don't know if we should stop recording, but I had to hide the truck camper somewhere on my property. So there's like trees and shrubs, and I hid it under there. It was like in MASH when they put those like camouflage nets over stuff, right? So the problem is that the Starlink dish can't see the sky. So I had to take the dish off and put it on the roof of my home. So every couple months I get up the ladder and I carry the dish up there and I lay it out there and I plug everything in and it says, oh, I've got an update, and downloads, and then after half an hour I can put it away. So what I realized as I got back towards this way, I was like, oh, I don't want to put the Starlink dish in the middle. I want to put the Starlink dish on the corner so I can more easily access it. So what you'll notice here is that, like, right, the pattern changes halfway. Because when I got to here, I said, oh, I don't want the Starlink here, I want the Starlink here. So I just changed which panels went where. Okay, so that's why it looks kind of funny that way. And here's just a rack I welded up. This is a detachable rack that holds 2 motorcycles. Summer of 18, I said, I want to travel, and my son said, I want to go to summer camp. So I said, how much is summer camp? So he said, it's $3,200. So I said, well, for $3,200, I can buy 2 Chinese motorcycles. They come in a box, and you put them together, and we can spend the summer motorcycling Montana. So he said, oh, I don't need to go to summer camp. So we bought the 2 motorcycles, and I built this rack to carry them, and this is like a snowplow light kit because the motorcycles block the lights. So this is wired in, and there's like switches under the hood that switch the lighting from the built-in lights to the lights up front. Okay, so here's the solar layout. As I mentioned, we have 3 panels at 185 watts each. And then we have 11 panels at 100 watts each. And so the total here is 1,655 watts. And short of, making like deploying solar wings or something like that, or getting rid of the Starlink, that's sort of, we're limited by what's on the roof. Now, I put this piece of wood here because I was a little bit concerned. If you've ever driven down the highway and stuck your hand out the window, there's a tremendous amount of force on it. So what this does, hopefully, I mean, it's been this way for 5 years. So any force is going to be, kind of down. I didn't want air getting underneath here and then lifting the panels off because the roof is water damaged. And so those beams that go across, I'm not terribly confident in how well secured they are to the roof. If you were to try, like lift the truck camper by the solar panels, that would be bad. So that's why I put this piece of wood. Okay, I've got 3 charge controllers. This is the charge controller from the original RV, which ran the 385 watt panel. So this is a Morningstar. This is like a commercial grade, like a really nice solar controller. And I have the panels in a 1S configuration, which means 1 serial, meaning they are just in a straight line. And just like if you've ever put batteries into an appliance where it has like 4 or 6 batteries, you'll notice that it kind of goes like the plus to the minus, the plus to the minus. And then if there's like a bar over here, they'll turn the other direction, right? It goes like minus, plus, and then minus, plus, minus, plus. And the reason it's doing that is it's electrically, they're all connected end to end. Okay, and that's called serially connected. And what that does is you add up the voltage and you do nothing with the current. Okay, so I have 3 36 volt and 5.14 amp panels. This, if you multiply this together, you get 185 watts. And by putting them in a serial configuration, you get 108 volts because it's 3 times 36 and 5.14 amps. The battery, which we're going to talk about in a moment, is for the sake of our discussion, it's a 26 volt battery. And so the solar controller converts the 108-ish volts that come off the roof to a lower voltage to match the battery. And like I said, the wattage stays the same. So when the voltage goes down, the current goes up by a corresponding amount. So we are dividing the voltage by 4 approximately. And what that means is that the current gets multiplied by 4. So these 3 panels theoretically are putting 21.34 amps into the battery. Now that is like if the sun is directly overhead and there's 0 atmospheric interference. So practically speaking, you're getting quite a bit less than that. And if you're curious what the difference is, there are actually I don't have a URL, but there's websites where you can select your location in the United States, and it will tell you how many watts per day on average you will get. So if you tell it I have a 100-watt panel, it'll tell you how many watts per day you're going to get over the course of that day based on the angle of the sun and the average cloud cover, etc. Next, we have the solar controller, which was originally used back when I only had 4 panels on this, and that's a 30 amp solar controller. And what I did was I took 8 of the 11 panels and put them into a 2 parallel 4 serial configuration. So what that means is that I've got 2 panels, and the plus and the minus, the plus and the plus are attached to one another, and the minus are attached to one another. And what that does is it makes it like one bigger panel. And then these 4, right, I have 8 little panels, which I made into 4 big panels. Then those are connected serially to one another. All right. So what's going to happen is when we connect 2 of them in parallel, the voltage stays the same, but the current doubles. So we would go from, I have 8 of these 18-volt 5.56 amp panels. And so now I have 4 18-volt by 10.12 amp panels. And when I take these 2 panels, which are then 1 panel, and I connect them serially, then we multiply the voltage by 4. And so we end up with this. And this gets converted to this. Now, you'll notice that 30.77 amps is above the rated limit of this solar controller. But I don't remember if there is like an engineer, if there's a, if you go over the limit by a certain amount, it's still safe. It's just that you don't get that charge. Or if I just said to myself, well, I'm never going to be in conditions that are sufficiently ideal that I will ever achieve 30.77. Practically speaking, I never will achieve over 30 amps, and so I didn't worry about it. I don't remember what the situation was. And the reason you'll notice that this nice, and I'll explain why this is nice later. This is a 45 amp. It's only managing 21 amps, and this 30 amp is fully loaded. And the reason is because these panels, when hooked up in serial, are at 108 volts. And the Renogy cannot handle that. It has an upper voltage limit of like 80 volts or something. So, and the reason that, so then you'd say, well, why don't you just put them in parallel? And the answer is that my understanding is that for my recollection when I was doing all this is that for shading, if you have panels that are partially shaded, like there's a tree or a cloud or whatever, it is better to have the panels be in series, not in parallel. And so that's why whenever possible, I put them in series and not in parallel. So this is 3 panels. This is the 3 big panels over here, 8 of the 11 little panels over here. And then for the 3 remaining, I just bought a 20 amp version of this. And those 3 panels are in serial. And so you end up with 11 amps going in through that. Okay. All right. So that's that. So all this current is going into the battery. So what is this battery? Well, here's the battery. This is a plastic milk crate, and it just happened to work quite nicely. These are, I have 8 304 amp hour lithium iron polymer cells. I purchased these cells individually from China, and it took them quite a while to get here. And they come with these bars, bus bars that you use to attach them together. And so if you follow from the red to the black here, right, this is a battery, just like a AA battery you put in an appliance or whatever. So you'll see it goes plus to minus, and you can follow along, and they're all in a line, okay? So each one of these batteries is 3.7 volts. And so when you put 8 of them in serial, it's 3.7 times 8, which is more than 24, but we're going to call it a 24-volt battery for now. Because flooded lead batteries, like in your car, are 12 volts. So people talk about 12-volt system, a 24-volt system, a 48-volt system. And so this is, in quotes, a 24-volt system. And the battery in total is 7.8 kilowatts. Okay, so you can take a look if you're curious at what a Nissan Leaf battery or a Tesla battery is, and this will, you can see compared to that how big this is. This box over here with all the wires, that is the battery management system. And what that does is it makes sure that so this device is actually measuring the voltage on every cell individually to make sure that they are balanced, that they all stay roughly the same voltage. And it has under voltage protection, so it will disconnect power if you draw the battery down too far to avoid damaging the battery, or if you attempt to overcharge the battery, it will disconnect that as well. And it has a Bluetooth interface, and so here's just an example of what that looks like. And you can see the voltage of each of your cells and how much current you are putting in or taking out, and the current state. So the battery is currently at a 42% charged state. And you can see the battery's temperature, total voltage, and it's not doing any balancing right now. If the cells right now you can see that they're within 0.005 of a volt of one another, which is pretty good. If it goes much higher than that, there's a bunch of resistors in the BMS which will consume some power. And so that will, for the batteries that have too much voltage, it will apply the resistor to that cell by way of these wires to reduce the voltage of that cell to bring them all in line with one another. Because depending on the health of the cells, they're not identical, and so that's what balancing is for. And then this is just a relatively inexpensive generic Amazon 2000 watt inverter, and its job is to convert the battery into 110 volts AC, so that I can plug in household appliances in the truck. Oh, and I seem to have messed up the animation. Okay. The next component here, the last piece, is the air conditioner. This is a 9,000 BTU air conditioner. It's a residential mini split, inverter based. It has a efficiency rating of 23 SEER2, which I think is sort of middle of the road. And it uses R410A, which is a refrigerant which is being or has been pretty much phased out. So I don't know how much you know about how this, basically you run cooling lines and electric lines between the outdoor unit and the indoor unit. And this is what you can see behind me right here. It has a Wi-Fi interface, so I can control it using the Smart Life application, which can also be used to control all of these Wi-Fi light switches and things like that. So I can be, I was out on a trail run in the middle of the prairie in northeastern Colorado, and when I got within about 2 miles of the camper, it was getting quite warm. It was going to be 104 that day. And so it was already approaching 90. And so I pulled out my phone as I was running, and I just turned on the air conditioner so that by the time I got to the RV, it would be comfortable. By the way, you're all over here, which is why I keep looking in this direction. Okay, so let's talk about, so that's that. So I'm just going to talk about some issues. And the biggest issue here is voltage drop. Okay, so voltage drop, if you've ever tried to drink a milkshake through a coffee stirrer, you understand voltage drop. What voltage drop is, and you can try this, go out to your favorite ice cream shop. It'll be very instructive. What happens is the copper wire is not a perfect conductor. And so as you shove more and more current through the wire, that current can simply not pass through that diameter of wire, and the wire's resistance, the less copper you have, the more resistive the wire is. And if I have sort of like a wire of infinite size, so then no matter how much I put into it, everything can flow through nicely. But if I try to push too much current through a wire that's too small, much of the current is consumed as heat. And so what ends up happening is that the voltage that appears at the end of the wire is not the same as the voltage at the source. This is why jumper cables are the size that they are, right? The reason that jumper cable wires are not like dental floss size is because when you try to jump a car, a massive amount of current is being sent from the good battery to the bad battery. And so we need very thick wires in order for that electricity to actually get to the battery. Okay, so when you design a system like this, and that's another reason, by the way, that when you do solar, you want the panels on the roof to be in series, because what I want, you'll notice that what I said was that voltage drop happens the more current you try to shove through a wire. It doesn't matter what the voltage is, it's only the current. So if solar panels are in series, I've got a very high voltage and a very low current, which is great because then I can use smaller wires to bring that electricity. It's the same wattage. I can use the same electricity to bring that to my solar controller. Okay, I mean, this is why if you think about, for example, a hair dryer, 1500 watts, that's quite a bit, but the cable of your hair dryer is much smaller than your jumper cables. And that's because your household voltage is 110 volts. So for 1500 watts, I'm only sending 1/10 of the current across the wire relative to your car, right? For that same 1500 watts on your car, you'd be sending something like 125 amps across those wires, and so you need jumper cables. But for your home, because voltage is 10 times higher, the current is 10 times lower, and so the wire can have a diameter which is considerably less. Okay, so once the voltage is coming off the roof, and you may recall that the voltages were quite high, right? You don't want to put this in your mouth. But they get converted to this 26 volt voltage, which is quite a bit lower, and these currents are higher. So I used quite thick wire. It was like 2 gauge and 4 gauge. So this is like jumper cable level stuff, and perhaps even a larger diameter. So the voltage drop is negligible. It's only a few tenths of a volt. Oh, and the other thing I forgot to mention is that voltage drop is proportional to the length of the wire. And because of the limitations of the truck camper, I ended up putting this milk crate. This is actually bolted to the floor under the refrigerator. And the solar controllers are under the sink, which is on the other side. So I need about 3 feet of wire. So I thought to myself, well, 3 feet of wire at a 4 or 2 gauge, which is like the diameter of your thumb, like it's quite big. The voltage drop, we're talking like 1/10 of a volt, big deal. But it turns out it is a big deal because the voltage curve of lithium iron polymer batteries is very flat, meaning that the voltage, the state of charge, meaning how much battery you've got, let's say at 60% on a 24 volt system, let's say at 60%, it's 26.6 volts. And at 90%, it's 26.8 volts. Well, that means that the difference between 60% charge and 80% charge is only 0.2 of a volt. So when you're trying to push a lot of current, what ends up happening is the battery's at 26.6, but the solar controllers are detecting that it's really at 26.8 because there's that resistance, right? You're trying to shove, in this case, you're trying to shove milkshake through a coffee stirrer. And so the solar controllers say, oh, the battery's full. And so they stop. Now, when they stop, they decrease their current. When they decrease their current, there's less current going through, so the voltage drop decreases. So they go, oh, battery's not quite full. So they start up again. So what ends up happening, practically speaking, is that the amount of current you're sending tapers off. But it tapers off way too early, like when you're at 60% charge. I want the battery to be like at 80% charge. This is a known problem, and the way this is solved is by using what's called a sense wire. So the way a sense wire works is it's a separate set of wires that you attach to the battery, and the solar controller has a separate set of terminals. And because the current that's going through those is very, very small, the solar controller, the only current going through the sense wires is enough current to detect the voltage of the battery. There's negligible voltage drop. And so now your solar controller has an accurate picture of what the battery is really at. The issue is the Morningstar, remember I said that's a commercial grade solar controller. The Morningstar has terminals for sense wires. These Renji ones do not. Okay. So there's no real way other than getting I can either move the Renji controllers closer to the battery, I can use bigger wires, or I could go to a higher battery voltage. so the smaller wires would have less of an impact. I came up with what I think is a clever solution. So, which I'll share with you. So with lead acid batteries, like the kind in your car, when, I don't want to get this backwards, but I might get this backwards. I feel like when it's cold out, you have to charge them at a higher voltage. And when it's hot out, you have to charge them at a lower voltage. So the solar controllers have what's called temperature compensation. And there's actually terminals on both the Morningstar and the Renogy for a temperature probe, which you kind of tape to the battery. And if it's a lead acid battery, it's going to use the temperature of the lead acid battery to decide how much voltage it should charge it with. Okay. And the temperature compensation is at an order of like 30 millivolts per 1 degree Celsius. So if the battery's 25 Celsius, now we go to 26 Celsius, it's going to go from sending it, 13 volts in a 12-volt battery, 13 volts to 13 volts minus 30 millivolts. Okay. So what I realized I can do, I haven't done this yet, but what I realized I can do is I can take like a microcontroller, like an Arduino, and I can measure the voltage at the battery and the voltage at the solar controller. And based on the difference, that tells me, okay, battery's at 26.6, but the solar controller is seeing 26.8. So then what I would do is the solar controllers that don't have sense wires, the Arduino would basically mimic a temperature probe. And the Arduino would tell the solar controller, oh, the battery's very cold. So it would tell it that enough degrees have dropped that the solar controller would then up the voltage it's trying to push into the battery by 30 millivolts per degree Celsius. So if I raise it by 10 degrees Celsius, imaginarily, the solar controller thinks the temperature has gone up by 10 degrees Celsius, or I'm sorry, has decreased by 10 degrees Celsius. So then it will compensate by 30 millivolts times 10, which is 300 millivolts, which is 0.3 volts. And so now the solar controller is pushing 0.3 more volts than it's supposed to. But at that level of current, that 0.3 volts is going to disappear in voltage drop. And so the voltage at the battery is going to be correct. And so in real time, I think I can just have this Arduino constantly measuring the difference in voltage between the battery and the solar controller, and constantly tricking the solar controllers into thinking that the temperature is constantly changing, which will cause the solar controllers to constantly compensate their voltage they're sending, so they're always sending the correct voltage to the battery. So I haven't tried this yet, but that's what I came up with. Okay, future plan. So here is the big RV, and we are considering eventually going full-time in this. And so, of course, the first thing I did was measure the roof. And it turns out I can fit about 5 kilowatts of panels on this. This is a 36-foot fifth wheel. The internal length is 36 feet. As you can see, it has 3 bedrooms here and 2 baths. We've since converted this bathroom into a home office, and this into a living room, where this slide out is actually a garage. So this has a door on gas struts, and the paramotor and the bicycles live in here. And we've got, it came with 2 rooftop air conditioners. I put a third one on. We're going to remove those 3 and replace those with 2 or 3 residential mini splits, and go from a 24-volt battery to a 48-volt battery, which would be 16 cells, so twice the storage capacity, about 14 kilowatt battery, if I remember correctly, and maybe even go to, instead of having 16 cells in parallel, in serial, we would have pairs of batteries in parallel, and then those pairs of batteries in serial. So let's say 32 cells in a 2x16 configuration, so it's 48 volts. But the rated amp hours would be 304 plus whatever the second cell that is paired with each of my 16 cells, if that makes sense. And then I would switch to they have really quite nice solar controllers now, which have an integrated inverter. So I don't need to have a separate inverter, and the efficiency of these inverters is much higher than the one I have now. Is about 75% in worst case, which is really quite bad. These all-in-one units have a built-in inverter, and also they have a grid input, where you can select the current. So this is for like if I'm at someone's house and I want to run my air conditioners and I don't have enough battery, so I can say draw 4 amps from the house and then the rest use my battery. Well, what I can do is I can buy a tiny little, this is quite small and fairly light. This is an inverter-based gas generator. And in the past, I've converted these generators from running on gasoline to propane, so they can run on the onboard propane supply. And then, this is rated to 2200 watts. So I would tell the charge controller only draw 2200 watts. And in this way, if I'm on the Oregon coast and it's been cloudy for 15 days straight, I can charge the battery with this light and small inverter, and I can draw the maximum that this generator provides, which means I can run it for the shortest possible amount of time. If you find any of this interesting and you want to do further reading, all of our RV adventures and modifications are on our website, lookbeforeyoulive.com, and there are a number of categories. So I think the RV mods, RV geek stuff, and RV repairs would be of most interest. But the trip map is there. And again, you can click on that and see what happened on every individual day. So I hope that this was somewhat in line with the spirit of this lecture series. And if you have any questions, please. Yeah, Howard, go ahead.
I guess my first question is, have you, on your new unit, replaced the refrigerator with one that is not running on propane? And what about non-propane cooking?
Right. So it is the case that I think now, if you were to buy an RV today, I think the refrigerators tend to run on 12 volts or 120. They don't typically put, I think, propane refrigerators into RVs anymore. In the truck camper, it is still the propane refrigerator. Getting these refrigerators in and out of the RV is really difficult. You can check out YouTube, because they essentially build the RV around the refrigerator. And so to take it out afterwards is a major headache. And the advantage is that if you get in a pickle, so now I can run the fridge off of propane, and that frees up more of my battery to run the air conditioner or other stuff. So that it does seem to me to provide some kind of flexibility, but it is true that a non-propane refrigerator would be more efficient. So someone asked in chat, are the motorcycles EV? No, they are 250cc gas burning motorcycles. Yeah.
Okay.
So is there any chance of you're getting cooking appliances that run on electric?
In the big RV, we actually ripped out the 18-inch wide propane stove oven, the range, I guess, and the cabinetry around it, which gave us a 36-inch wide hole, which was very convenient because we actually went out and bought a residential self-cleaning gas range. It comes with a kit, and you can tweak it for propane instead of natural gas, and installed that instead. This is back when we were doing the 3-year trip back in the 2013 to 2016. It was a terrifying moment when we were on the middle of our road trip, so we're in Las Vegas or something, and got the gas range back to the RV and realized that I had not bothered to measure the width of the door. Well, RV doors are not as wide as your house door, but I was able to take the door off the range and remove all the knobs, and we were able to slip it in there. So we do have a full-size residential gas range, which is very nice. Yeah, now many RVs don't even come with ovens anymore. They just come with a cooktop, and some of them are like an induction cooktop. It's not something I've really looked into. The truth of the matter is that once you're heating, because remember the mini split here does heating as well as cooling. So once you have taken heating off the table, the propane seems to last quite long. In other words, I've been on the road now for 5 weeks, and I have not even used up a single 20-pound cylinder of propane. So, is it something? Yeah, I guess really it's just a cost benefit analysis, and at this point, I don't see the benefit.
Ben, a quick question on the solar panels, just that you've driven them thousands of miles in all sorts of weather. And did you have many challenges in terms of maintenance and environmental situations that required repair or special maintenance?
Yeah, so not the panels themselves. The panels themselves have been fine. I was thinking about what happened, and I think the answer in short is that I'm not an aeronautical engineer, so I don't really understand cycles before failure, right? So if you're making an airplane, you have to worry about if I pressurize and depressurize this thing 10,000 times, what happens, and how far can the wing bend before the wing breaks? Well, these struts here are exposed to 65 miles an hour plus whatever the wind speed happens to be. And so what I did find, and I think these are made of, if I remember correctly, like 1/16. It's rather thin aluminum. It's like a 1 1/4 by 1 1/4 L channel, but rather thin aluminum. And so, yes, I actually did have a couple failures along these beams, mostly because if I was doing this again, you'll notice that they're attached at the ends and then at the center. But what really I should have done is the center supports here really should be along these lines. Okay, and so the supports are like here, but what ends up happening is that this seam here is where the panels seem to kind of do this, and they put a lot of weight right here on the midspan. And so in a couple places, I have had to go up there and just double up, cut a length of aluminum L channel and double it up here. So I carry, I have a rather large toolbox to carry with me. And every summer I look at the angle grinder and I say, this is stupid, I'm never going to use this. And then every year by day 10, I've used it already. So I carry a couple 8-foot lengths of this as well as an angle grinder. And I did actually do a repair at the Cracker Barrel of Des Moines, Iowa this summer, because that's where I slept for the night. If you ever need a place to sleep for the night, Walmart and Cracker Barrel are your go-tos. Someone asked in chat, any major blow up or major funny snafus? They're not funny at the time. But yeah, RVs are horribly underbuilt. I think there's sort of a race to the bottom in terms of who can make it cheapest. And so with this RV, for example, this RV weighs almost 8 tons. But the difference between what it weighs empty and its rated capacity is like 1,000 pounds, which is kind of ridiculous considering that it has 160 gallons of wastewater as well as 50 of fresh water. Well, that's 250 gallons of water. So guess what? That weighs almost 2,000 pounds. So you're already without even people in it or any stuff in it, if you have it full of water, it's overweight. And so, yeah, on our 3-year trip, we had a leaf springs brake. We had an axle perch brake, which is, there's like a little piece that attaches the axle to the leaf spring. So the axle just slid back until it came in contact with the frame of the RV. And this happened on the single lane road called the Top of the World Highway between Dawson City, Yukon and Chicken, Alaska. And so, yeah, we ended up pulling off the side of the road, and I had to spend, I believe it was maybe 5-6 hours, 4 to 5 hours driving to the nearest parts place, which was in Tok, Alaska, and buying three bottle jacks and some extra leaf springs and fixing it on the side of the road. We had a wheel come off on the Kenai Peninsula, all the lug nuts broke. And so, yeah, we've had some pretty pretty interesting misadventures with that. So in the middle of the trip, I went from a 6-leaf spring to an 8-leaf spring, which meant I had, and because the 8-leaf springs were a different length, so then I had to replace the equalizer, which is this like piece that the 2 leaf springs attach to. And so now the trailer rides a bit higher. So yeah, there was a whole bunch of yes. So the truck camper, it's on top of this Ram truck, which is built to like haul around mounds of gravel. So it seems to be fine. But these things are just so poorly engineered, and there's like a class action suit now because the frames are cracking, and it's So yeah. Okay, well, thank you very much. I hope this was interesting and informative.
I'm just going to say, wow.
Hey, Ben, when are you going to make that a mass production business? Go IPO.
No. I'm perfectly happy earning money teaching computer science and then using that to buy solar panels and stuff like that.
And you're going to continue to do it.
I hope so. Yeah.
We have 808 at the time, but I'd like to share very quickly a few things.
Can you see this?
I can see the zeroing out home carbon emissions. Yeah.
Is that what you want?
Yeah, that's good enough. So I'm going to skip over a section. It'll probably be in the stuff I sent up by email, but the sections concerning the Conestoga type solar solution, which is like yours, but in spades. It's like even more convoluted than yours. It was invented by somebody who lives near us, and but I'll put that in the later material sent out. I wanted to mention that we have a major goal, which is a move away from fossil fuel to clean electricity. And this slide shows all the aspects of a fully electric house with solar panels on top, the insulation below, it's weatherized. All these things that are in this house and surrounding are things that our electrification coaches care about. And so, next slide. And so for those of you who find yourself in very complex situations, Ben was in very complex situations, but we have coaches available for you to help you preserve your health, save money, and reduce greenhouse gas emissions. And we call ourselves the New Jersey Electrification Coaching Network. We've been running for close to a year, I guess. Next slide. So we have going forward. Next slide. Oh, okay. And so what you can do if you have questions about any of these aspects of electrification, we have free coaching available and a large number of coaches throughout New Jersey. If you can tell us what your problem is, you can get a free electrification coach to help solve your problem. Ben doesn't have that luxury, but you all do have that luxury, and we have coaches available who are trained and can help you. You just have to answer these 5 questions. Was that the last slide, or is there one more? Okay.
No, not that, right?
Not that one. Well, this is the complex thing. So I think that's the end of our recording. What I want to do is to stop the recording and leave this slide up, because you can go to the Scan Me with your phone, and it will take you to that tiny URL link. I'm going to stop recording now. But thank you all on the recording for joining us, and we'll see you next event.